So last session, we stopped here with generative adversarial networks. The big picture was going beyond maximum likelihood estimation and perhaps trying to minimize nicely chosen divergences. One of them could be Jensen-Shannon divergence, but minimizing the Jensen-Shannon divergence directly is not feasible. That's why you need to seek help from a discriminator. So a neural network is going to train another neural network, or a neural network is going to define the loss function for another neural network. But this is not the only functionality of your discriminator. You can actually use it to do feature learning, because in the end of the day, the discriminator is looking at some images, let them be real or fake, and maybe by the last layer, it is learning to featureize your images in one way or another. And that's exactly the topic of this paper. You can actually do unsupervised representation learning. When we were doing image classification in part 1 of the course, for those of you who took it and for those of you who are going to take it next semester, we had the ImageNet data. And for ImageNet data, you have pairs of input, output. Your input are images, your outputs are classes. Maybe you have 1,000 classes. And you were doing your feature learning using that data set. And basically, that was a supervised learning framework. This is going to end up being unsupervised representation learning. And in the end of the day, you're going to learn to take an image as an input and output a vector. And once you have your vectors, then the last layer could just be a simple logistic regression. The video is online, so I'm not going to spend too much time on this paper. But what is the big picture here? First of all, we know that training GANs is not easy. One solution to that is perhaps go ahead and modify your architecture, or go ahead and modify your loss function, or modify your training process, perhaps use a different optimizer. This paper is going to focus on the architecture, and it's going to give us some guidelines, like replacing pooling layers with strided convolutions. And if you are going from low resolution to high resolution, use fractionally strided convolutions, use batch norm, remove fully connected hidden layers where you have your deep architectures so that you have fully convolutional network. Use ReLU, use ReLU. So these are the suggestions that the paper is making, and it's able to generate relatively speaking high quality images for that time. The only thing that we don't know is what is fractionally strided convolution. Fractionally strided convolution is going to enable you to go from low resolution to high resolution. So you're going to keep increasing the resolution from one layer to the next one. And all a fractionally strided convolution is, it is the derivative of a regular convolution. And that is the math that you see here. This is the exact formulation of fractionally strided convolution, taking you from low resolution to high resolution. And there is some equivalence with the derivative of a convolution or a strided convolution. At the same time, some nice things happen if you look at your generator and the latent space of your generator. All of these images are generated. So you know their corresponding z's. You take those z's, average them, push them through your generator. That's going to give you an average face of a man with glasses. You do the same thing for a man or multiple men without glasses. Then you add a woman, and then you're going to end up with women with glasses. So this part was all about the generator part. How do you actually do unsupervised representation learning? You're going to look at your discriminator, which is going to go the reverse route of your generator. It's going to take an image as input, and then it's going to output the vector. Now the question is, are you going to use the features at the last layer? Are you going to use features at this layer, at the previous layer? What are you going to do? And the paper is using all of them. But if you want to use all of them, some of these are high resolution, and then your last vector that you're going to work with after concatenating all of these is going to end up being a huge vector that we don't like. The features from the previous layers, you're just going to divide them into 4 components. or 4 windows, and then you're going to average locally in that 4 windows. So each one of these layers is going to give you 4 vectors, and then you concatenate them and use them as features. And on top of that, you can put a simple classifier like support vector machine or even logistic regression. So not only the job of the discriminator is to train a generator, it can also featureize images. That's the idea. Any questions about DCGANs? So if you go online to PyTorch or TensorFlow repositories, this is one of the first tutorials, this architecture that you are gonna notice on GANs. Okay, is everything clear? Okay, perfect.